So our next definition is cardinality. If a set A is a finite set, then the cardinality is, and you can think of n as the counting function or the number of function. So n of A equals the number of elements in the set. So remember, when we're talking about a set, we're never allowed to repeat elements. So in example 1, we're asked to determine the cardinality of each set. Well, the number of elements of the set A are 1, 2, 3, 4. So n of A is 4. The set tossing a coin twice contains heads and tails. So the number of things in S is going to be 2. And then finally, the empty set, remember, is the set that contains no elements. So the number of things in the empty set is going to be 0. So for cardinality, we're just asking how many elements are there in a set. So turns out that counting is hard. There's really no other way to talk about it. Counting is difficult to do. So as a set becomes larger, counting the items in the set becomes more complicated. This leads to the idea of breaking sets into smaller, more manageable parts and counting those. So given two sets A and B, find A union B. There are two cases that we need to analyze. What are they? So if we want to talk about counting the elements of a set, what are the two possibilities that we could run into when it comes to counting? Well, the two possibilities are if A intersect B is the empty set, or if A intersect B is non-empty. And the reason for this is when we union two sets together, we're saying all the things in A or all of the things in B. Well, if A and B share elements, would I just be able to add together the number of things in A and the number of things in B? The answer is no, because the union says we only list them once, which would lead to overcounting. So our possibilities really come down to these two things. So if A and B share some elements, if we had the number of things in A union B, we would like this statement to be true, that it's the number of things of A plus the number of things in B. Right? Because A union B is the stuff in A or the stuff in B. So the only way this is going to be true if A intersect B is the empty set, because then they would have no overlap. But what if A and B had some common elements? So let's see what happens. What if I have the set A contains the letters A, B, and C? And what if I let the set B contain the elements B, C, and D? Well then, what is the number of things in A? 3. And what is the number of things in B? Also 3. Let's calculate a couple of things. What is A union B? Well, that would be A, B, C, D. And what is A intersect B? That would be BC. So then, how many things are there in A union B? 1, 2, 3, 4, right? And how many things are there in A intersect B? 1, 2. So if we try our formula, the number of things in A union B is equal to the number of things in A plus the number of things in B. Well, the number of things in A union B is 4 is equal to 3 plus 3. Well, is that statement true? No, that statement's not true, right? The number of things in A union B is not the same as the number of things in A plus the number of things in B. Well, why is that the case? Well, A had A, B, and C, and B had B, C, and D. But the union has only A, B, C, and D. So what happened in this equation? Well, B and C were both in A and B, right? This is in A, this is in B. Oh, that's this part right here, right? So if B and C are in both sets A and B, that means how many times were they counted here and here? They were counted twice. So that means I overcounted. And how much did I overcount by? Well, if I counted B, C twice, that means I overcounted by 2. So then to correct this, I would need to subtract the things that they have in common, or 2. So the number of things in A union B is equal to the number of things in A plus the number of things in B minus the number of things that they have in common. In terms of a Venn diagram, let's see what this picture looks like. So our intersection has the elements B, C. Our set A has A, B, C, and our set B has B, C, D, right? So how many things are there total in this Venn diagram? 4, right? A, B, C, and D. When I count the number of things in A, I count A, B, and C. When I count the number of things in B, I count B, C, and D. But I counted B and C, the stuff in their intersection, twice. I counted it once with A, and I counted it once with B. So to correct that, I have to subtract off the things that were counted twice, which is A intersect B. So that is our general formula for calculating. So as mentioned, A union B is equal to n of A plus n of B if their intersection is empty. Because if the two things have no elements in their intersection, then just adding their two things together will work, because we're not double counting anything. All right. So let's do some examples. So let A be the set heart, club, diamond, spade, and let B be the set heart and diamond, and let C be the set A, B, C. So how many things are in the set A? 4. How many things are in the set B? 2. So how many things are in the set A union B? Well, what is A union B? Well, A union B is going to be all the stuff that's in A or the stuff is in B. But everything that's in B is also in A. So A union B is just going to equal A. So it's going to be heart, club, diamond, and spade. Which happens to also be the set A. So how many things are in A union B? 4. How many things are in A intersect B? Well, A intersect B is going to be heart and diamond. Good. So we get 2. The number of things in B is also 2. Number of things in C is 3. And the number of things in C union B, well, we check that B intersect C. Well, heart and diamond share nothing with ABC. So their intersection is empty. So then this is equal to the number of things in C plus the number of things in B, which is 2 plus 3, which is 5. And the number of things in C intersect the number of things in B. It's empty, so it's going to be 0.
Isn't it? So C union B.
So in a recent survey, 60 students living in Harris Hall were asked about their enrollment in science, engineering, and humanities classes. The results were as follows. Okay, how many students are not taking a science class, an English class, or an engineering class, or a humanities class? So what do we know about the size of our universe? 60, right? Our universe contains 60 students. We're then given some data. 24 students are taking a science class. 22 students are taking an engineering class. 17 students are taking a humanities class. 5 are taking both science and engineering. 4 are taking both science and humanities. 3 are taking engineering and humanities. And 2 are taking all 3. We want to know, well, how many are not taking a science class, an English class, or a humanities class? So basically, how many people are not taking any of those 3 classes? So we need to fill out our Venn diagram. So when we're given data like this, it's best to work from the inside out. So if somebody is taking all 3 classes, that's going to be the intersection of all 3 of these, right? So let's go with, call this science, call this engineering, and I'll call this one down here humanities. So how many students do we know are taking a science class, an engineering class, and a humanities class? Yeah, but go to the very bottom. We know 2 are taking all 3.
Okay.
So that's what goes in the very, very center, because that's the and of all 3 of those. We then want to look at the one above that, which says 3 students are taking both engineering and humanities. So engineering and humanities is going to be right here, right? That's the intersection of engineering and humanities. But this already has 2 students in it, and what do we need the total to be? 3, right? Because it says 3 students are taking both engineering and humanities. So yes, in this place we're going to put 1, because now in that intersection there is a total of 3. Our next one is 4 students are taking both science and humanities. So science and humanities, that's this intersection. And we have a total of 4. We've already accounted for 2, so that means we're going to need 2 more there. We keep going. 5 are taking science and engineering. So we're probably getting the hang of this by now, but that's science and engineering. And how many people need to be in that intersection? Yeah, 5 total, so 3 are going to go here. Perfect. So now we've figured out these parts. We can use the top 3 to finish filling in our Venn diagram. So 17 students are taking humanities, right? Well, if 17 students are taking humanities, how many have we already accounted for? 2 plus 2 plus 1 is 5. So then that means there must be 12 down here. Doing something similar, how many are taking an engineering? Well, that's going to be this circle. And we've already accounted for 3 plus 2 plus 1 is 6. So 22 take away 6 gives us 16. And then we have our last one, which is science. We know that there are 24 students over here. And we have 3 plus 2 plus 7. 3 plus 2 plus 2 is 7. Apparently skipped that last number. And 24 take away 7 is 17. So this gives us our Venn diagram. Well, now if we add up all of those numbers, how many students do we have? Well, let's see. 17 and 3 is 20. 16, 2 and 2 is 20. So that's 40, 41, 53, right? How many students were in our universe? 60. And if our Venn diagram accounts for 53 of them, yeah, so 7 of them are in this universe, aka Harris Hall, but they are not in science, engineering, or humanities. So in this case, there are 7 students. All right. So we knew our universe had 60 students in it, and we wanted to find the students that weren't taking a science, engineering, or humanities class. Well, if we unions together S, E, and H, we got 53 students. The complement of science, engineering, and humanities would be the things not in any of those 3, purple, green, or blue, right? And that left us with 7 things. So we were able to count the complement of that set. It turns out that this is often very useful. Sometimes certain things are very, very hard to count, but their complement is not. In which case, we can use it to indirectly find that number. So the cardinality of a complement. If S is a finite universal set and A is a subset of S, then the number of things in A complement equals the number of things in the universe minus the number of things in the set A. And vice versa, the number of things in A is equal to the number of things in the universe minus the number of things in A complement. So basically, we have that relation because a set plus its complement has to take up everything in the universe. Because remember, an element's either in a set or it's not. So if it's in A, okay, we counted them. And if it's not in A, that takes up the entire space when you add those together. So that gives us the relationship that the number of things in A plus the number of things not in A has to equal everything in the total space, and then just subtract to get these two equations. All right. Let's take a look at example number 7. Or example number 4. The table shows sales in millions of items of Macs, iPhones, and iPads sold by Apple in 2012, 2013, and 2014. So we've got this table. We want to find U prime, A intersect U prime, A intersect U prime, and C union U. All right. So let's talk about each of these sets. So the set U would be what? That's this row. The set U would be the total number of Macs, iPhones, and iPads sold in 2012. Okay, well that's this value, 201, right? But we want its complement with relative to this. So what's our total? So our universe has our total number of sales. So the number of things in our universe is 695. So then the number of things in U prime is going to be the number of things in the universe take away the number of things in U, which is 201. So that gives us 494. So now we want the number of things in A intersect U, and then its complement. Okay? So what is our A intersect U going to be? Well, let's do A is this way, and U is this way. So what is A intersect U going to be? 18. So in terms of that, A intersect U is Macs sold in 2012, right? But now we want its complement. So according to this set, if we want A intersect U complement, well, that's going to be everything but the Macs sold in 2012, right? So what's that going to be in terms of our sets when we want our number? Well, how many things were sold total? 695. Take away, how many Macs were sold in 2012? 18, right? Because it's the intersection where they overlap, right? A intersect U is where the set A and the set U have things in common. The set A was Macs sold in 2012, 2013, 2014, and their total. The set U was Macs sold in 2012, iPhones sold in 2012, iPads sold in 2012, and their total. So the and is where the yellow and the blue meet, which makes green, which is 18. Right? The and is, it has to be in both sets. The only thing that's in both sets is the Macs sold in 2012. The union would be the either set. Right? So we have to be a little careful, which is what we're going to look at now. If we look at our last one, we have C union U. So C union U, C is this column, and U is this column. So what is it going to be? Are those two sets disjoint? No, so it's the number of things in C plus the number of things in U minus the intersection of C and U. So it's going to be 197 plus 201, take away their intersection, which is 58. So 197 plus 201, take away 58, and we get 340. All right, so the last thing we want to talk about is the cardinality of a Cartesian product. So if A and B are finite sets, then the number of things in A cross B is the number of things in A times the number of things in B. If we look back at our Cartesian product from last time, that should make sense because we modeled them by making a rectangular array. Listing the number of elements in set A and the number of elements in set B gave us a rectangle that told us the number of things that were in the set. So a 2 by 6 gave us 12 elements. A 3 by 2 gave us 6 elements, and so forth. So this theorem is just that diagram telling us that. So let A be the sample space of tossing a fair coin once, and let B be the sample space of rolling a fair die once. Find the cardinality of, well, if A is tossing a coin, how many events are in our sample space? 2. And if B is rolling a die, we have 6 possible outcomes. So then the number of things in A cross A, well, A cross A, according to our thing, is N of A times N of A, which is N of A squared. So that's going to be 2 squared, which is 4. Right? Because head, tails, head, tails. You're going to have 4 elements in your table.
So it's not multiply times 2, it's squared.
Well, you got to multiply them by each other. In this case, anything times itself is going to be squared. Keep watching. Okay, what is A cross A cross A? Well, applying that rule 3 times, that's N of A times N of A times N of A, which is going to be N of A cubed. So 2 to the 3rd power is going to be 8. Okay, so the number of things in B cross B is the number of things in B times the number of things in B, which is 6 times 6, which is the same as 6 squared, which is 36, right? Similarly, B cross B cross B is going to be the number of things in B cubed. So 6 to the 3rd power is 216. The number of things in A cross B is going to be the number of things in A times the number of things in B. So that's 2 times 6 is going to be 12. Oh yeah, I'm pretty sure we made that diagram earlier, right? So then, what about A cross B times A cross B?
So 12 times
Good. So this is the same as the number of things in A cross B times the number of things in A cross B, which is the number of things in A cross B squared. So we just figured that out. So 144. So we're going to skip that one because we already did it. So our next one is A cross A cross A cross A cross A cross A cross A. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of things in A cross A 10 times is going to be what? The number of things in A raised to the 10th power, which is 2 to the 10th power, 1024. So if we know the cardinality of the underlying sets, calculating the Cartesian product of the number of things is easy. We just multiply them together. If we repeat the same set, i.e. with itself, how many things would there be? So just to give you an idea, what would the set A cross A cross A cross A cross A represent?
A to the power of n is.
Right, but what was our event A? We were tossing a coin, right? So what that would be is, imagine your sample space would then look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you tossed the same coin 10 times, what would be how many possible outcomes are there?
There's 2 outcomes and 10 times.
Well, for 2, but if we had to do it 10 times, well, I could roll all heads, so 10 heads in a row, or flip 10 heads in a row, not very likely. Another event would be I'd flip 10 tails in a row, not very likely. And then maybe I could flip 1 head and 9 tails. But then the order they're arranged in here could be done a whole bunch of different ways. So what this 1024 says is that if I were to create words, I'm going to use that, using only 2 letters with length 10, how many possible words are there using T and H that are 10 letters long? 1024. Right? There's 1024 different ways I could write down something like head, tail, tail. Like this would be I flip a head, a tail, a tail, a head, a tail, a head, a head, a tail, a head, a tail. That's one possible outcome of me flipping a coin 10 times. There are 1023 other ways that could happen, right? That I could flip a coin 10 times and get an outcome. That's what our 1024 represents, is all of those possibilities. All right, we are under 60 seconds left, and that is the last thing.